we have shown that ZPP is in RP and coRP. But what we did is we constructed this M prime by truncating the computation after a while, right, 3 times the expected runtime. Now we want to show the other side, which is RP intersection coRP is in ZPP. So we will have 2 algorithms and we will run them together. Let's do that. So let L be now in RP intersection coRP. It be decidable. Let L be decidable by probabilistic Turing machines M1 respectively M2 in time polynomial in n to the c for constant c. So let's define a new PTM M. So what will M do? It will simulate both M1, M2. So pick random R. Run M1 on X with this with random string R as the random choices, and M2 XR. Okay, you can do this sequentially. First run M1 X comma R, store the answer, then run M2 X comma R, store the answer. And if the answers are the same, remember that these two are RP coRP machines, so they will stop after some after this time, right? N to the C we have assumed. So after N to the C steps, they will stop. Then you check whether the answers are the same. If they are, you should output the common decision. So if both of them said yes, say yes, output yes. If both of them say no, output no. So intuition for this is on a yes string, RP machine, the coRP machine, which is M2, on a yes string, M2 will give the correct answer. And on a no string, M1 will give the correct answer, right? Because there is one-sided error. So that is why if both the answers are the same, then you have the correct answer. Else, you don't know what happened, so you have to abort and repeat the experiment. So you have to go to step 1 and then repeat this experiment. Okay, so let's analyze. Suppose X is a yes string. So M2 has to say yes. Or maybe I say 1. I'm identifying 1 with yes always, right, and 0 with no. So M2 has to say 1 because M2 is coming from the coRP property, so it cannot make a mistake on yes instances, it has to say yes. And what that means is probability over the random string M1. What can you say about M1? So M1 will not be yes, will not be 1. With small probability. The error probability of M1 making a mistake is small. Okay. So yeah, so on the yes instance, M1 may make an error. This is by definition. Okay, you take this as a definition of M1, M2. So M1 makes an error on yes instance with low probability, and no error on the no instance. That we will use in the second case. And M2 in the yes instance doesn't make an error. So M2 will say yes, and M1 may say no. Now if M1 also said yes, then you will exit and output the correct answer. If it says 0, then this algorithm M has to be repeated, right? Step 1 will be repeated. So let's analyze that case. So what happens in T steps? So in T rounds of step 1, you get the probability over these choices R1, RT. M1 always saying 0, okay, which means M1 making a mistake again and again T times. That is smaller than 3 raised to T, 1 by 3 raised to T, right? Because every time you are using independent random strings, so error probability is 1/3 multiplied that many times. So which means that the expected number of rounds so there will be T plus 1 rounds, meaning that the first T were all wrong, so that is probability 1 by 3 raised to T, and T can go from 0 to anything, right? There is no upper bound on how many rounds there will be in this algorithm M. But notice that this T over 3 raised to T is actually, even with infinitely many steps, it is this is a bounded quantity. This is actually constant. Okay. Just do this as an exercise. So sigma 1 over 3 raised to T is bounded by 2, and even T by 3 raised to T sum is bounded, because this denominator is growing much faster than the numerator basically. So number of rounds is expected to be constant. Okay, so think of 10 rounds. So in 10 rounds you expect a correct output in step 3, and which means that the time complexity is pretty good. That's what you reduce. So this implies that the expected time complexity of M on X, okay, this is polynomial in n to the C. So it simulates M1, M2 and simulates it infinitely many times, infinite many steps, but in actually the expectation is only polynomial. And the case of x not equal to L is similar. Okay, so in both the cases, yes or no strings, M has a good expected time complexity, which means that we have shown L in ZPP, which means that any problem in the intersection is in zero error. Okay, so that is what property 2 demanded. And from property 2, you immediately get that ZPP and RP intersection coRP are equal. Okay, that follows easily. Okay, so that is a very good comparison. And the open questions are, yeah, whether P and ZPP are the same, and the other side. So let's state the open questions. So it is the conjecture we make is that actually P is equal to ZPP, and similarly the conjecture we make is ZPP is not NP intersection co-NP. Okay, but these are open questions. So ZPP should be closer to P than from NP intersection co-NP, but it's not known. None of these two things are known. So next thing we will discuss is error less than 1/3, less than equal to 1/3 in BPP important. Can we talk about error any constant below half? Okay, or let's say polynomially close to, inverse polynomially close to half. So what about error less than equal to half plus, let us say, n to the c? Okay, in terms of input size x and some constant c. So this is inverse polynomial. So if you are very close to half, by very I mean inverse polynomial, then is this error too big, or will you still get BPP? Okay, you can ask about these questions. This is related to what is called probability boosting or probability amplification. We now show how to boost the success probability. How do you boost it? You boost it by repeating the same experiment. Okay, you repeat the experiment again and again and then take a majority vote. So this is the topic of probability amplification. If you have done a probability course before, you would remember Chernoff bound. Okay, so we essentially will use Chernoff bound and show that majority vote is good. So what we will show is, what you will see in the end is that the 2/3 in the definition of BPP so this was in the definition of, also in RP we had 2/3. and in BPP we had 2/3. Yeah. So 2/3 in the definition of probabilistic classes. Is arbitrary. Okay, so in fact we can use any fraction that is inverse polynomial away from half. Okay, so you need an advantage more than half, which is just inverse polynomial advantage. Okay, you don't even need advantage like 2/3 or strictly bigger than half by a constant. So that's a very useful theorem to have. So this is the amplification theorem. So let probabilistic Turing machine M decide L such that for all x is in L if and only if probability that MXR is 1 over the random bits R, random string R, is just marginally more than half. So it's half plus 1 over x to the c. Then for all d there exists a probabilistic Turing machine M prime such that for every input x is in L if and only if probability that M prime accepts x, the success probability is significantly more than half, it's close to 1. Okay, so this is close to 1. So the point is, if you start with success probability close to half, just above half, then you can boost it up almost to 1. Okay, so starting from a success probability just above half, you can reach just below 1. Okay, obviously this just above and just below you have to quantify. We have quantified it properly. So above half you need inverse polynomial advantage, and then you will reach 1 by an exponential amount, inverse exponential. So this is a very strong theorem. Okay, this is inverse exponential. So it is approaching 1 rapidly as you look at bigger and bigger inputs, right? So for practical purposes, this is really no error. Okay, it's 100% correct answer, almost. So how do you prove such a thing? So details of this really fall in probability courses, so I'll not go into those details. Algorithmic idea is simply that you take this probabilistic Turing machine M and run it t times with independent R's, independently chosen random strings, and then so every answer will be yes or no. You take the majority vote. So if yes appears more than t by 2, you output yes, otherwise no, and this answer will really be robust. Okay, it will have a very high probability of success. That's the key algorithmic idea to remember. So run M k times on X with independent random bits or random strings and output the majority value. And in the probability analysis, use Chernoff bound. Use Chernoff bound to analyze the error. The error probability. Okay, so let's define this new algorithm or PTM. So define this new PTM M prime as follows with so we'll pick k to be large but not too large. That will come from Chernoff bound actually. So let's take k to be 8 times the size of x raised to d plus 2c. What are c and d? So c is this inverse polynomial advantage over half, and d is this inverse exponential distance from 1 or closeness to 1. Right. So based on that, you define k, and then as I said, just repeat. So and repeat in majority. So on input x, run mx k times with independent choices. Okay, so the IID is for independent, identically distributed random bits. So let the outputs be y1 to yk. Okay, respectively for each execution of mx. Just output the majority of this. Okay, so y1 to yk are 0, 1 or yes, no, whichever appears more than k by 2. To break the tie, you can think of k to be odd. Okay, I can just define here k to be this, and so k is odd, and hence there will be either yes or no will be in the majority, clear majority. Use that. So M prime is very easily defined, right? using M, it's just repeating the experiment M many times. How do we analyze the error probability now? So let's do the analysis. So for I 1 to K, define xi. So define this random variable xi to be 0 if yi is wrong, and 1 otherwise. If yi is right. Right, so xi is just an indicator variable. Now since yi comes from a random process, so we can call it a random variable. It's 1 if yi was correct, 0 if yi was wrong. And what we are interested in is, you can think of it as summation xi. So what is sigma xi? In fact, we are interested in what is the chance that sigma xi is it's a sum of zeros and ones, right? And we want ones to be more than k by 2. So what is the chance that that doesn't happen? It's less than k by 2. That's the bad event, right? That the number of ones is actually less than majority. So you want to estimate this probability, that's the error probability, based on the success probability of M, or the error probability of M was just below half, right? Inverse polynomial away from half. So based on that, we will estimate this sigma xi next time using Chernoff bound.